Hello everyone. Today I'll talk about the solution to the problem maximum width ramp. This problem has a very simple statement. We want to find the two values that are the furthest away in our array, such that the left value is less than or equal to the right value. I'll present one way of thinking about this problem, but there are other solutions, and I encourage you to think about this problem yourself, think about other solutions, and to that end I'm not going to probably be too specific here, because it's really a nice, simple problem to state, but educational to think about. So the key idea in problems like this is that there is a notion of domination within the array. And by domination I mean that there are some values in our array that render other values obsolete, that make it such that the existence of one value means that some other value will never be a part of any pair that can create, in this instance, the widest ramp. And I suggest that you think, when you look at problems, about this notion of domination, because it's very easy to see it. The final algorithm might not be that easy to see, but the fact that there are some elements dominated by other elements is often easy to see. Because, for instance, in this case, it's very clear. We want to have the left end be less than or equal to the right end. So if we here have a value of 4, maybe, and here we have a value of 5, then we know for sure that this 5 will never be a part, or will never be the left end, more specifically, of any good ramp. Because if something to the right of the 5 is bigger or equal than it, then we can create a ramp not with the 5 as the left end, but with the 4, and that ramp would be better. And we can always do it, because this thing, this x, was for sure greater than or equal to this 5. And typically, when we have a problem where some elements dominate other elements, then we have two approaches that can, well, there are multiple approaches that we can use typically. One approach is probably some form of binary search. In order to have some array on which to binary search, that array will typically be either a prefix, some prefix operation, prefix maximum, prefix minimum, or the same from the other side, suffix minimum, suffix maximum, or it's going to be a monotonic stack. And also, often when we have prefix maxima and minima, or when we have a monotonic stack, then instead of solving the problem using binary search, we can solve the problem faster, not in n log n, but in linear time, by just doing 2 pointers, or in terms of the monotonic stack, we can typically just have a single pass through the stack. So, to make sure that we're clear, the monotonic stack is just a stack such that only interesting elements are on that stack, and an interesting element is an element that is not dominated by any other element. So this 4 is, of course, so let's say that this 4 is interesting, then we know that this 5 is not interesting. And so essentially we only want to keep those elements on the stack that do not have a smaller element to the left of them. And that's why the name monotonic stack comes into play, because that stack will be sorted. More specifically, and let's say that because typically we also want to remember the position of our values, the only thing that can be next is a value that's smaller than the 4. So there is, let's say, some 3 on some other position, then maybe a 1 on some other position. So this stack will be decreasing. And it matches our intuition, because if we have some right end, then we want to create as long a ramp as possible. So we have to try, so we want to try maybe taking the first element of the array. And we have to balance those two things. We want to have something that's as far to the left in our stack as possible, whose index is as small as possible, but it has to be smaller than we are. So here is where a binary search would happen. So now if we have a value of, let's say, 2, then you can binary search here, which is the first value that's smaller than the 2. So it would be this 1. But also, if we have that monotonic stack, then we can typically do it in linear time and a single pass. And the monotonic stack is of course very similar to prefix maximum and minimum, and this is the solution that I'm going to present. That's because essentially the prefix maximum or minimum is the same thing as the stack, but instead of keeping only the elements that are not dominated, we keep an element or the element that dominates our current element. So we keep this 4, maybe again 4, now this 3 happens, then 3, 3, and then 1 to the end of the array. So for every element we know which element dominates it. And as we can see by definition of this stack, that this is simply the prefix minimum array. So every position is just the minimum on that prefix of the original array. And so finally we reach the smallest element, and then the prefix minimum is the smallest element to the end. And the final thing that we need to solve this problem is to come up with an idea how to operate on either our stack or this prefix minimum array. And it's quite simple. We want to go through all the elements in our prefix minimum array or in our monotonic stack. And we also want to maintain a pointer to the element to the right of our array. And we don't want to move that pointer to the left, but sometimes we have to move that pointer to the left, and we have to move it to the left when it becomes smaller than the value that's currently a prefix minimum. So let's say that in our array here we had a 1, then we had a 2, then we had a 3. So we know that with this one, we're happy to keep the right end as this 3. And let's change that 3 to a 2. Because in this case, we're going to have to change our value when we reach this 3. So we want to keep using this 2 as the right end for as long as possible. We can do it here, we can do it here, we can do it here. And this thing provides us with a ramp that has the difference of 2. And now we can't use it here because it's smaller than this value. So we have to look to the left until we reach a bigger value. This 2 is wrong, this 1 is wrong. But this value might be correct, might be incorrect. But since the 1 started here, so this thing is 3 or 4 or 5, something else. So we'll keep this value. And again, this value will be met here, here, here. We're going to get the ramp. Then we have to change it now, or maybe we don't have to change it. Maybe we've reached a bigger value immediately. So we go through those 4s and so on. So this is the same thing as just going through this monotonic stack. And this is the thing I want you to think about, because a monotonic stack is quite unintuitive in many cases, but it's a powerful technique. Prefix maxima, prefix minima are also very interesting, and it might not be immediately clear how to utilize this domination to solve the problem fast. To calculate the prefix minima, we can do it very easily in linear time. Here I'm going to showcase something that we can do in Python, which is not common in other languages. We can iterate through the array of nums with v as our value. And now we want that v, so the value that we want to append to the prefix minimum is either v or the previous minimum. And we can do it starting with an empty array, and now we check. If the array is non-empty and the previous minimum is smaller than our value, then we should insert the previous minimum, not the value, so we can just write v equals to the last element in prefix minima. So we change this value as we're iterating over the array, but in Python it doesn't matter, because iteration works in such a way that it's at the beginning of every step of the iteration, it just changes the value of v to the next value produced by our iterable. And again, we're going to start with our 2 pointers at the end of the array. Remember the best result. And now we'll be stepping step by step through our array of prefix minima, so until we cannot do it anymore. And we have to make sure that the right pointer, which again starts at the back of the array, is always at least as big as the corresponding prefix minimum. And you of course don't want the 2 pointers to cross each other. So we have to move to the left, our right pointer, for as long as we have to, until we reach something that's at least as big as our prefix minimum. And of course, after we reach that point, we can update our result. And of course, at the end, we return that result, which is the maximum over r minus l for every point. So for every l we do it. And that's why the solution has linear time.